Welcome to Dialogues in Science and Technology, the podcast where lab breakthroughs meet everyday life. Today we're unpacking single-molecule sensors and the fast-moving field of biosensing and molecular diagnostics, tools that spot disease earlier and power precision therapeutics. From safer food to cleaner environments and healthy people, these nanoscale sentinels are reshaping how we detect, decide, and treat. Grab your curiosity. Let's make science and technology conversational.
Welcome, deep divers. Today we're plunging into the really tiny world of single-molecule sensors. Imagine going from just the city census data to seeing the unique story of every single resident. That's kind of the leap we're talking about, witnessing individual molecules directly.
Exactly. And our mission here really is to explore how this huge shift in measurement isn't just, a lab curiosity. It's actually revolutionizing fields. Medicine, environmental protection. It gives us insights we just never had before.
Okay, let's unpack that. For ages, science looked at ensemble averages, like trying to understand a crowd just by its shadow, right?
Well,
what were we missing?
Oh, a lot. The crucial reality of individual differences. Ensemble measurements, they just hide all that variation, the heterogeneity between molecules that look identical. And importantly, they can totally miss rare, but really critical things, like an early disease marker that's maybe 1 in a billion.
Oh, okay.
Single molecule analysis brings these hidden behaviors right out. It finds that needle in the haystack.
So it's not just about seeing smaller things, it's seeing clearer, finding stuff we literally couldn't detect before. And what about things happening quickly, dynamic processes?
Precisely. Yeah, it lets us watch biological processes in real time, like a single enzyme folding or unfolding, or a molecular motor actually doing its job, without that blurring effect you get from averaging everything together. It's a much more granular picture, like going from room temperature to tracking every single air molecule's path.
That makes sense. But what I'm really wondering, and I bet you are too, is how? How on earth do you see just one molecule? It sounds almost impossible.
Yeah, it does. The whole field is basically built on winning this signal versus noise fight. It boils down to two main things: extreme confinement and really specific detection. We shrink the observation volume down dramatically, sometimes to zeptoliters.
Zeptoliters, wow.
Yeah, it's tiny, like 100,000 times smaller than a standard microscope can even see. Techniques like nanopores, these incredibly small holes, or using plasmonics, kind of light tricks with metals, they physically or optically trap single molecules.
So we're building like nanoscale cages or stages to isolate them? That's incredible engineering.
It really is. And it's given us this amazing toolbox. Optically, we've got super resolution microscopy, things like DNA paint. It lets us build up these super detailed images, nanometer by nanometer. And then there's the whole label-free revolution, which is very exciting.
Label-free. That means no bulky tags messing with the molecule's natural behavior.
Exactly, you got it. Techniques like plasmonic nanoparticles, they can sense a single protein binding just by a tiny shift in light. Or SIRS, surface-enhanced Raman scattering, gives you a unique chemical fingerprint of a molecule. No labels needed, but it's not just light. Electrical methods are also super powerful.
Okay, tell us about the electrical side.
Well, nanopore sequencing is a big one. It reads DNA or RNA directly, molecule by molecule, just by measuring tiny changes in electrical current as the strand goes through a pore.
Right.
It gives us these ultra-long reads, great for sequencing whole genomes without errors, and it can even spot chemical modifications on the DNA itself. And then pushing it further, things like single electron transistors can give, like an electronic fingerprint of individual gas molecules, ultimate sensitivity.
So what does all this amazing tech mean for us in the real world?
Oh, the impact's huge, especially in medicine. Take early cancer detection. There are platforms like Simoa Single Molecule Array that can literally count individual biomarker proteins.
Count individual ones?
Yeah. Imagine finding that one specific marker in like a swimming pool full of blood. Simoa boosts detection limits by maybe 1,000 times or more. It means liquid biopsies can find tiny traces of tumor DNA way, way earlier than we could before.
That's genuinely life-changing potential. What about outside of healthcare?
Well, think environment. You can have a nanopore sensor, maybe embedded in a hydrogel, that detects a single pesticide molecule in the air. Instant pollution alert. Or for security, detecting explosives like TNT at picomolar levels, that's incredibly low, using these electrical single-molecule methods. Safer communities, safer planet.
Okay, these sound almost too good to be true. What are the big challenges? The hurdles?
Well, the tyranny of diffusion is definitely one. Just getting enough of those rare molecules into the tiny sensor volume quickly enough That's tough. And making them work reliably in messy samples, like blood, biofouling stuff sticking to the sensor is a real headache. We need robust quantification, not just detection.
Right, making it reliable and quantifiable. So how are we tackling that, and what's coming next?
The future's looking really exciting. AI is becoming crucial for handling the massive amounts of data these things generate, and we're using semiconductor tech, CMOS, the same stuff in our phones, to put billions of these sensors on tiny chips, super cheap.
Billions, wow.
Yeah, making it scalable and affordable. And maybe the most exciting part, this tech is moving out of the lab. Portable devices, smartphone microscopes, democratizing this high sensitivity analysis, making it available potentially everywhere for everyone.
So from a tiny flicker in a lab to potentially personalized medicine diagnostics in your pocket, single molecule sensors are really shifting our view of those building blocks.
Absolutely. It's this convergence of super sensitive hardware and smart AI. It's more than just new tools. It feels like a new era of molecular intelligence is dawning, giving us incredible insights into our health, our world. The real question is, what will you do with the power to see the unseen?
Thanks for listening to the podcast on Dialogues in Science and Technology, that is PDST, and our deep dive into Amazing World, the revolutionary single-molecule sensors. Stay curious and see you next time.